Hello, everyone. Good evening. Welcome to today's MCAT review session. So today we're going to be going over Jack Weston full-length practice exam number 5, and we're going to be going over the chemistry physics session. We're going to be going over passage number 5. So as per usual, I'm going to be breaking down the passage, reading it, highlighting the pertinent information, and then I'm going to be going over the questions. Okay, for those of you who don't know me, my name is Daniel Menasia. I'm a fourth year medical student, MD class of 2025. So, yeah, without any further ado, we're going to get right into it. And I'm going to start sharing my screen here in a second. Sec. All right. So, without any further ado, let's go ahead and get started. Okay. So, we're going to be doing questions 22 through 25. We might do a little more just because there's questions without passages. And sometimes, some students like to go over those as well. So that's what we're going to be doing today. All right. So I'm going to go ahead and start reading the passage and, follow along, pay attention to the things that I highlight. I'll also be talking about them as I go along. Okay. Compounds in the vapor phase can be assumed to follow the ideal gas behavior, or to follow ideal gas behavior. Okay, so when we know in this passage, we're going to be using the ideal gas law. Okay, so whenever you see ideal gas, just start thinking about the ideal gas law. Okay, an experiment was performed to determine the molar mass of an unlabeled volatile liquid by analyzing its vapor phase properties. Okay, so an experiment was done. What was the purpose of the experiment? We're going to determine, excuse me, the molar mass of an unlabeled volatile liquid, and we're going to do that by analyzing its vapor phase properties. Okay, all right, highlighting that. The methodology followed a specific protocol, okay, and relied on the ideal gas law, which I just mentioned, for calculations. Okay, so for those of us who don't know, the ideal gas law is one of the most high yield equations that you have to know for the MCAT. So the ideal gas law is just simply PV is equal to nRT. And, it's so simple that even I still remember it, even though I took my MCAT like 6 years ago. Okay, so or over 6 years ago. All right, so moving on, a 125 milliliter Erlenmeyer flask, okay, housing a small quantity of dithiazone crystal was employed. All right, so 125 milliliter Erlenmeyer flask, okay, we might need that for a volume calculation. Housing a small quantity of dithiazone crystal, okay, which is probably either an indicator or a catalyst, was employed. It was carefully sealed with aluminum foil and copper wire, and its mass was measured at, and its mass was, 91.10 grams. Okay, cool. Subsequently, 5 milliliters of the liquid sample was precisely measured into the flask with the foil cover tightly crimped, tightly crimped. Okay, yeah. So the foil cover tightly crimped, and a pinhole was introduced to the foil. Okay, cool. Let me just highlight that as well. All right, so the experimental setup involved a water bath arrangement. If you know what a water bath arrangement, a lot of people have taken, Gen Chem, OChem. So some people might remember what a water bath arrangement looks like. If you don't and you see this, don't stress out, don't freak out. You don't necessarily need to know every single detail in a passage to be able to answer the questions correctly. Okay, so if you know what a water bath arrangement looks like, great, awesome. If you don't panic, don't stress, keep a level head. Okay, utilizing tap water with a 600 milliliter beaker atop a wire gauze on an iron ring. Okay, the temperature carefully controlled to approximately 125 via a Bunsen burner, so 125 degrees Celsius via the Bunsen burner. The pressure of the room was recorded at 1013 millibars. Okay, so 1013 millibars. Okay. The flask, securely clamped and tilted, was immersed as deeply as possible in the heated water bath. Now they're just describing their experiment to you. Heating continued until the diathiazone's green color completely disappeared. Okay, indicating indicating full vaporization of the liquid sample. Okay, cool. So diathizone was an indicator. Following the temperature recording, the Bunsen burner was turned off and the flask was allowed to cool. Post-cooling, the flask's weight was determined as 91.42 grams. Okay, so I'm guessing, yep, it was 91.10, now it's 91.42. Cool. Its volume is measured at 160 milliliters using tap water in a graduated cylinder. All right, cool. So 160 milliliters. I think this is the most important volume in the entire passage. This is our final volume, most important mass, final mass, using tap water in a graduated cylinder. Okay, the molar mass of the compound was calculated, assuming it's an ideal gas. Okay, again, ideal gas equation, ideal gas law. Okay, remember. So try to memorize your most high yield equations, your equations of motion, your ideal gas law, other gas equations that are important. Yeah. Okay. So, and if you need like help, study strategy, I've helped countless of, you know, younger, not necessarily younger, but, MS1s, MS2s, kind of newer med students, stabilize their study strategies, know when to employ, active recall, know when to employ spaced repetition, know how to manage the large volumes of information. So if you need help with study strategies, feel free to reach out to me and I will help you come up with good study strategies to help you cover the most high yield material you need to know and be able to retain the material long term with deep understanding. Okay. All right. So next, excuse me again. Next, 10 milliliters of the compound was mixed with okay, potassium dichromate, I believe. But just looking at it, it's an oxidizing agent. Um, this is one of those things via XP. So XP just stands for experience points. So, and there's a lot of questions like that, things from just gaining the experience points, practicing, doing questions, seeing problems. And yeah, so it comes up pretty frequently as an oxidizing agent. So yeah, potassium dichromate. Okay. In an acidic solution and bubbles are formed in the liquid. Okay, cool. So our passage pretty much, ended right here. Okay, next, 10 milliliters of the compound is mixed with potassium dichromate in an acidic solution and bubbles are formed in the liquid. Okay, cool. So now question 22. When treated with potassium dichromate in an acidic solution, the compound was, we already established this is an oxidizing agent. So the answer is oxidized. It wouldn't be reduced because this is not a reducing agent. So oxidation, remember, oxidation is loss of electrons. Reduction is gain of electrons. So if something is an oxidizing agent, well, think about it, right? Something is an oxidizing agent. It's going to want to oxidize things. Okay. It's going to want to oxidize things. And what is oxidation? Loss of electrons. Okay. This was a reducing agent. It would want to reduce things. And what is reduction? Gain of electrons. Okay. It wouldn't be acidifying anything because there's no sort of basic base. that that made sense in my head, but I think saying it out loud, there's no sort of like there's no way for this to be or to acidify anything because it doesn't have any like I guess protons to give, even though the thing is in an acidic solution. So oxidizing agent is gonna want to oxidize things, and oxidation is lost. So yeah, no, esterification, there's no carbons in this even. So the best answer is A. Okay, so yep, oxidized, right? So potassium dichromate, strong oxidizing agent, can oxidize other substances. Okay, given the bubbles were formed, gas was released, of course, sign of redox reaction occurring. Okay, let's see, after reviewing, blah, blah, blah. Okay, so again, reduction is the gain of electrons. And since potassium dichromate, it is accepting electrons, again, because it's an oxidizing agent and oxidation is loss, right? Loss of electrons is going to help whatever it is interacting with get oxidized, which is it's going to help it lose electrons, right? So, okay. Yeah, that's literally just it. A lot of people understand that. 77% of people got this question right. So yeah, great. All right, I'm gonna move on to the next question real quick without wasting much time because I don't want to make this video too long. All right, so the reason for introducing a pinhole into the foil was A, determine the volume of the compound more accurately. No. Very much no. Um, decrease the pressure in the flask until the room pressure. Yes. Good. Yep. Very good. Most likely the answer. C, determine the pressure change in the flask to find the molar mass. No. We already know the molar mass. It was calculated. They told us that in the passage. Okay. No. Increase the pressure to determine the deviation from the ideal gas. No. Everything in this vignette, that forgive me for using that language because yeah, anyway, medicine stuff, forget that. So everything was pointing to the fact that we're keeping and assuming ideal gas situation, right? So it appeared three times: ideal gas behavior, ideal gas law, ideal gas, assuming it's an ideal gas. So like, no. Okay, so the most correct answer, the most likely answer, is B, because um the pinhole was created to decrease the pressure of the flask until it matched room pressure. Simple. That's kind of, yeah, yeah, that's pretty straightforward. 79% of people got it right. Good job. Okay, so ideal gas law, PV equals nRT. Okay, assumes the pressure in the flask matches the surrounding pressure. So again, that's why we created that pinhole. Um, None of this is making sense, feel free to reach out to me or one of the other MIM MCAT tutors, and they'll be able to help you sort of better understand and interpret what these questions you're asking. Okay, pretty straightforward question. You want to decrease the pressure, don't want it to build up. That's why you put the pinhole in the flask or in the foil, rather. Okay, moving on.